Hi everyone, in this video we'll look at special products part 1. So written below here I've got a plus b times a minus b. And let's expand this and see what we get. So if we FOIL this, we get a squared minus ab plus ab minus b squared. Now if we combine the middle terms, which we could have done in our head and skip this step, we get a squared minus b squared. So anytime that you multiply what are called conjugates, these are called conjugates. Anytime you multiply conjugates, the middle terms will be opposite in sign. So you'll end up getting what's called a difference of squares. So this is called a difference of squares. Difference of squares. It's called a difference of squares because a squared is going to be a perfect square, b squared will be a perfect square, and so when you subtract a perfect square from another perfect square, another way of saying that is that's just a difference of squares. So we can use the symmetric property of equality to go from from a difference of squares into something in factored form. So difference of squares will always factor into conjugates. So let's go ahead and use this identity here to factor some difference of squares. In the example below, it says factor completely. And in example 1, we've got x squared minus 4y squared. So notice here that we've got two terms. The first term is positive. The second term is being subtracted from the first term. And again, they're both perfect squares. So that means that they're going to factor this polynomial is going to factor into conjugates, or this binomial is going to factor into conjugates. So if we think about how to fill this in, well, we've got x and x here, and then we'll have positive 2y and minus 2y here. So this factors into the conjugate pair x plus 2y times x minus 2y. And if you want to verify that that works, you can go ahead and expand that, and you'll see that x times x is going to give me x squared. Positive 2y times negative 2y should give me 4y squared. And the middle term is going to be 2xy minus 2xy, which leads to us having a middle term that adds to 0. So we've factored this correctly. In question number 2, I've got 18a squared minus 98b squared. So remember that the first thing that you should always do when factoring is to look for common factors. So although 18 and 98 aren't perfect squares, if I common factor out 2, I get 9a squared minus 49b squared. So 9a squared is a perfect square and 49b squared is a perfect square, and I'm taking the difference between the two perfect squares. So that's a difference of squares, and it'll factor into the conjugate pair 3a plus 7b times 3a minus 7b. And if you're wondering how I came up with that so quickly, 3a is just the square root of 9a squared. 7b is just the square root of 49b squared. And I know that following my identity above, that it's going to factor into two binomials of this form. It's going to factor into a conjugate, product of two conjugates. So next I have, in question 3, x to the power of 4 minus 1. So x to the power of 4 is a perfect square. It's x squared. So x squared squared gives me x to the power of 4. 1 is a perfect square. So I can factor this by writing it as the product of the conjugates, x squared plus 1 times x squared minus 1. And again, I came up with x squared by taking the square root of x to the power of 4, and positive 1 by taking the square root of 1, or 1 and 1 by taking the square root of 1. And then I just wrote this as the conjugates. might think that you're done factoring here, but if you look in this bracket, we have another difference of squares. X squared minus 1 is another difference of squares. So we were asked to factor completely, so if you'd stopped at this step, you wouldn't have factored completely. So let's go ahead and we'll factor x squared minus 1. So we've got x squared plus 1 times x plus 1 times x minus 1, because x plus 1 times x minus 1 gives us x squared minus 1. These are a conjugate pair. And again, I got x by taking the square root of x squared, and I got 1 and 1 by taking the square root of 1. So next, let's look at a plus b squared minus c plus 2d squared. And when you're asked to factor this, it might be really, really tempting to expand this and then try to factor the expanded polynomial. But I assure you, if you do that, you're in for a whole world of hurt. So this actually isn't too bad. If you consider a plus b as a single variable and c plus d as another single variable. So we can introduce a variable. We can say on the side, we can say let, I don't know, x be equal to a plus b. And we can say, let's say, let y be equal to c plus 2d. Okay, and now we have x squared plus, minus y squared. Where I've just made a substitution here. I've just substituted for a plus b, I've substituted x, and for c plus 2d, I've substituted y. And I should have an equal sign here. So next I know that this factors into the conjugate pair x plus y times x minus y. And lastly, I can substitute back in for x, I can substitute a plus b, because x is just equal to a plus b. So I can rewrite x as a plus b, and I can write y as its original expression, which was c plus 2d. So I have a plus b plus c plus 2d. And then again, in this other binomial, I can substitute a plus b for x. So a plus b for x minus, and remember that when I make a substitution, I have to include brackets around whatever I should include brackets around whatever I'm substituting. So here I've got c plus d that I'm substituting for y, so I'll write bracket c plus 2d. And so now I can simplify, I can distribute the negative into c plus 2d, and I get a plus b plus c plus 2d times a plus b minus c minus 2d. And this just looks a little bit nicer than it did before. So that's completely factored. And again, you'll notice that that if you were to try to have expanded this first, you're trying to factor into, you would have had to have factored this product basically into a product of two polynomials that each have 4 terms. So that would have been really difficult to do. So it's definitely easier if you exploit this being a difference of squares. So in the last example, in example 5, we're going to factor 3x to the power of 4 minus 2x squared minus 1. And there's 3 terms here. So this definitely is not a difference of squares because there are 3 terms. So since there's a coefficient that isn't 1 beside x to the power of 4, and there's 3 terms, let's go ahead and we'll use a guess and check strategy. So we'll try to factor this into the product of 2 binomials. We'll try, well, this term and this term have to multiply to 3x to the power of 4. So we'll try 3x squared and x squared. This term and this term have to multiply to -1. So let's try, I don't know, let's try -1 and +1. And then we'll check to see that the middle term is correct. So remember that the middle term comes from multiplying. It's going to come from multiplying 1x squared and adding to that -3x squared. So if we multiply 1 times x squared, we get 1x squared minus 3x squared gives us -2x squared. So just by luck and a little bit of foresight, I factored this correctly. Notice here that we're not done though, because the question said factor completely. That means factor as much as you possibly can. And in the second binomial here that I factored this into, I have x squared minus 1, which is a difference of squares. So that means I can further factor this. So this factors to 3x squared plus 1 times x plus 1 times x minus 1. Because x squared minus 1 is a difference of squares, and it factors in the conjugate pair x plus 1 times x minus 1. That concludes this lesson, and we'll see you in the next video.